Hello, Math 109 students. We're moving on to Chapter 5. So we're skipping Chapter 4, going to Chapter 5. We're on the second half of the material for the course now, which will just cover Chapter 5 and Chapter 6. Chapter 5 is about how to solve, the big idea of it is how to solve higher order polynomials, especially those where we have to do something other than factoring to get the answer. But there's going to be a lead up to it. So the first questions on the assignment won't deal with that, but they'll lead up to it. I'm not doing Chapter 5 section by section, like 5.1 and then 5.2 and then 5.3 and so on and so forth. So I'm just doing it I'm just taking bits of all of Chapter 5 and putting it all together in one homework assignment. So you only have one assignment for Chapter 5, but it is 43 questions for that one Chapter 5 assignment. So I'm just going to go through all of the questions on the homework to teach you. And as we come to concepts, I'll go into those concepts more fully. This Chapter 5 video may be broken up into 2 or 3 different videos. All right, the first question on the homework: find the intercepts of the following equation. This is really not anything different than you've been doing. To find the x-intercept, you plug in 0 for y, and you then get x by itself. And then to get the y-intercept, you plug in 0 for x. And then you would solve by getting y by itself. So I'm not even going to go into that one because that's not new. That's something you've done already. So moving on to number 2. I guess that was just a review. All right. Is the expression a polynomial? If so, what is its degree? So we need to get a couple of vocabulary words. So what is a polynomial? All right. A polynomial has to meet 2 conditions. All right, the first condition is all coefficients must be real numbers. All right, all the coefficients, meaning all the numbers in front of the variables, must be real numbers. And the second condition that must be met is that all exponents must be whole numbers, also known as non-negative integers. So the whole numbers are, 0, 1, 2, 3, 4, 5. Those are the whole numbers. It can't be negative. It can't be a decimal. It can't be a fraction. The exponents must be the whole numbers, 0, 1, 2, 3, on and up. The coefficients just have to be real. They don't have to be whole. They just have to be real. They can be any real number. So can pi be a coefficient? Yes, because pi is a real number. It's irrational, but it's still real. Can 1/3 or negative 500 or negative 1.716 be a coefficient? Yes, because they're real. The only thing that can't be a coefficient is an imaginary number. So the square root of a negative, or if the number has an I with it, then it can't be a coefficient. Or if it is, then it's not a polynomial. So let's look back at our example here. Is this expression a polynomial? Let's look at the coefficients. 4, negative 3.6, negative square root 2. They are all real numbers, right? If the negative was inside the square root, it wouldn't be real. But since it's outside the square root, it is real. Look at the exponents. We have a 3 and a 2. Are they whole numbers? Yes, they are. Therefore, it is a polynomial. Sorry, I clicked the wrong button. I thought A said it is a polynomial. Choice B, it is a polynomial, but it also makes me say what the degree is. Well, I haven't taught you what the degree is yet. The degree is the highest, it's the coefficient, no, It is the highest exponent on a variable. That's what the degree is. The degree is the highest exponent on a variable. So what is the degree here? What is the highest exponent on a variable here? It is 3. Okay, state whether the following statement is true or false. The x-intercepts of a function are the real solutions of the equation f of x equals 0. That is exactly what an x-intercept is. An x-intercept is when you have 0 for y. 0 for f of x is the same thing. When the y value is 0, you are crossing the x-axis. So that is exactly right. If g of 5 equals 0, what point is on the graph of g? What is the corresponding x-intercept of the graph of g? Well, if g of 5 equals 0, then 5 is the x-coordinate. That's the input. And 0 is the output, or the y-coordinate. So 5, 0 is the ordered pair. The corresponding x-intercept is, you can simply put as 5. If r is a real 0 of even multiplicity of a function, then the graph of f does what? The x-axis at r. All right, there's a new concept I need to teach you. Let's say you had a function f of x, and let's say it factored out like this: x plus 3, x minus 1, x minus 1, x minus 5. So that's the way it factored. Okay, then we would have solution. Our solutions would be x equals negative 3 and positive 1, but it actually will equal positive 1 2 times, right? You would get positive 1 from both of these factors, because x minus 1 appears twice in the factorization. So you could say, you could put 1 down twice, or you could just put 1 down once. But if you put it down once, you just would need to understand that that is called a double 0, or a double root. And then also we would get 5. So the negative 3 appears only once, and the 5 appears only once. However, the 1 appears twice. Well, that's where the word multiplicity comes from. All right, it's the number of times the solution occurs in a polynomial. All right, so we could say the solutions are negative 3 with multiplicity 1, 1 with multiplicity 2, and 5 with multiplicity 1. So if you have even multiplicity, that means that it occurs an even number of times. The solution occurs an even number of times. So in this case, like in this example I've given you, it is the solution 1 occurs twice. So since that's an even number, it's an even number of times, it would have even multiplicity. When this is the case, the graph touches the x-axis without crossing. Okay, it touches the x-axis. I could draw that for you. So it would come down here and touch the x-axis, but it wouldn't cross it. All right. For odd multiplicity, the solution occurs an odd number of times. When this is the case, the graph crosses the x-axis. So an odd multiplicity, it would actually cross the x-axis. So if I did my example here, -3, 1, and 5, right? There are my x-intercepts. It would cross at -3, touch at 1, and cross at 5. So it might look something like that. It might not look exactly like that, but it might look something like that. So let's go back to our problem. If r is a real zero of even multiplicity of a function, then the graph of f does what? Touches or crosses? Touches the x-axis at r. If r is a solution of the equation f of x equals 0, name 3 additional statements that can be made about f and r, assuming f is a polynomial function. Choose the correct answer below. If r is a solution of the equation f of x equals 0, in other words, you set the y value equal to 0 and you solve for x, then r is a real zero of the polynomial function. R is a y-intercept of the graph of f. That is not true. It is not a y-intercept. It is a real zero, but it's not a y-intercept. So we can go ahead and eliminate choice A. If r is a solution to the equation f of x equals 0, then r is a complex zero of the polynomial function of f. R is an x-intercept of the graph of f. And x plus r is a factor of f. That is not true. If r is the solution, then it wouldn't be x plus r. Let me show you what I mean. Okay. If we have x plus r as one of the factors, then we would set that equal to 0, and solve it, and we would get negative r as the solution. So if we don't want negative r to be the solution, in this problem it says r is the solution, then actually x minus r would have to be the factor, because then you could set that equal to 0, and if you solved it, you would get x equals r as the solution. So let's go back to our problem, and let's read choice C again. If r is a solution to the equation f of x equals 0, then r is a real zero of the polynomial function f. That's right. R is an x-intercept of the graph of f. That's right. And x minus r is a factor of f. That is right also. Choice C is what we want there. Complete the sentence below. If f of x equals -3x to the 5th plus x to the 3rd minus 6x squared plus 9, then, and we have this strange looking notation here, this is called end behavior. The way that you read this is the limit as x approaches negative infinity of f of x equals what? And the limit as x approaches positive infinity of f of x equals what? All right, I need to teach you some serious concepts on this one. Okay. End behavior. All right. There are 4 cases. 4 cases, and they all have to do with the degree and the leading coefficient. So you remember what the degree is? The degree is the highest exponent. Well, the leading coefficient is the coefficient of the term with the highest exponent. H-I-G-H-E-S-T. The degree is the highest exponent. The leading coefficient is the number in front, or the coefficient of the term that has that highest exponent. The degree and the leading coefficient determine everything about the end behavior, because all the other terms are going to kind of bow down to that leading term. The term with the highest degree is going to take over when it comes to the end behavior. Okay, so when the term is in standard form, so if it's in standard form, the degree and leading coefficient occur in the first term. Because in standard form, you go in descending order according to the degree. You put the highest exponent term first, then the next highest, then the next highest, and so on and so forth. All right, now, if you have an even degree, okay, an even degree, so like x squared, or x to the fourth, or x to the 12th. What are you doing, screen? If you have an even degree, both arms point in the same direction. They either both point up or they both point down. So how do you know if they both point up or both point down? All right, let me go ahead and say this. If you have an odd degree, the arms point in opposite directions. Okay, so if the one arm will point up and the other arm will point down, like that or like that. Okay, how do you know which way it is? That's going to be the leading coefficient. Positive leading coefficient. Right arm up. Negative leading coefficient. Right arm down. Okay. All right. That's what you need to know. That tells you everything. Positive leading coefficient means the right arm's up. So if it's an even degree, that means the right arm's up and the left arm's up. If it's an odd degree, then the right arm is up, which means the left arm is going to be down. If it's a negative leading coefficient, the right arm is down. And so if it's an even degree, the left arm is also down. But if it's an odd degree, that means the left arm is going to be up. Okay. So let's say this. If it's an even degree, positive leading coefficient, then it's going to be something like this. And it may do all kind of stuff in the middle, but it doesn't matter about what happens in the middle. That doesn't matter. All I care about is the arms. Both arms are up. If it's an even degree, negative leading coefficient, both arms are going to be down. If it's an odd degree, positive leading coefficient, our right arm is up, might do all kind of stuff in the middle, don't really care, and the left arm is down. If it's an odd degree, negative leading coefficient, then the right arm is going to be down, the left arm is going to be up, and might do all kind of stuff in the middle, but the left arm is up and the right arm is down. So we would say the end behavior for this, let me shrink this down so I'll have some room to write. The end behavior we write like this. We say as x, we say let me see how they write it on Math Excel, so I'll do it the same way. Limit of f of x. The limit of f of x as x approaches, what does it put first? Because you can do this different ways. It says negative infinity first. As x approaches negative infinity, that means you look to far as you can to the left. You look as far to the left as you can. Don't worry about the middle. Just look at the left arm. X approaches negative infinity means look at the left arm. Okay? The limit of f of x as x approaches negative infinity, look at the left arm, is going to equal infinity because it's going up to infinity. The y value, f of x, y, is going up to infinity. And the limit of f of x as x approaches positive infinity is equal to what? Now, as x approaches positive infinity means you look at the right arm. So don't worry about anything but the far right arm. And where is that function going vertically? On the far right arm. It's going up to infinity. So it's going to be infinity and infinity for that one. What about for this one? The limit of f of x as x approaches negative infinity is what? I mean, so we look at the left arm. Where is the function going vertically on the left arm? Negative infinity. And the limit of f of x as x approaches positive infinity. Now you're looking at the right arm. What's it going to be? It's also going to be negative infinity. All right, let's look at the third case. The limit of f of x as x approaches negative infinity. That means I'm looking at the left arm. Where's it going on this one? It's going down to negative infinity vertically, so negative infinity. And the limit of f of x as x approaches positive infinity means I look at the right arm. Where's it going? Vertically to positive infinity, so that's equal to infinity. And finally, the fourth case, the limit of f of x as x approaches negative infinity means I look at the left arm and I say, where is this thing going vertically? It's going up to positive infinity. And the limit of f of x as x approaches positive infinity means I look at the far right arm and I say, where is this thing going vertically? And it's going down to negative infinity. So that's the summary of all the cases for end behavior for any polynomial. Now let's go back to our problem and do it. Look at the leading coefficient and the degree. The degree is odd, and we have a negative leading coefficient. That means the arms point opposite directions. The right arm points down, and the left arm points up. So if I'm answering this one, it says the limit of f of x as x approaches negative infinity. I'm only thinking about the left arm, and the left arm is going to point up. So my answer is going to be infinity. What is going on here? This is a shorthand way. You can click on infinity right here, or you can do a shortcut on the keyboard if you do the / or maybe that's a backslash, I'm not sure, but it's that slash and do INF, then it puts in infinity for you. And as x approaches infinity, that means I look at the right arm, and since this is negative leading coefficient, the right arm points down, that's going to be negative infinity. And that is correct. All right, again, determine whether the function is a polynomial function. If it is, state the degree. If it is not, tell why not. Remember the two conditions to be a polynomial. You have to have real coefficients and whole number exponents. The coefficients are 4 and 1. They are real. The exponents are 1 and 3. They are whole, so it is a polynomial. What's the degree of this polynomial? The highest exponent is 3. Polynomial of degree 3. Determine whether the function is a polynomial function. 1 minus 7 over x. All right, I need to tell you something about this one. Anytime, so let's say 1 1 minus 7 over x. Anytime x is in the denominator, you can rewrite that as x to the negative 1. So if this is x in the denominator, it can be rewritten as x to a negative power, and it just no longer be in the denominator. And since I can write it that way, okay, that negative 1 right there is not a whole number. It's negative. So it's not a whole number. It's not a non-negative integer, which is the same thing as a whole number. Not a whole number. Whole numbers can't be negative. So then let's go back to our problem. Is this a polynomial? No, it's not, because the degree of x here is not a whole number. So choice A, I think, is right. Not a polynomial because of the negative power of x. Negative exponent, negative power of x. All right, is this function a polynomial? Well, the coefficients are real, but the exponents, that 5/4 exponent, is not a whole number. Okay, so it's not a polynomial because 5/4 is not a non-negative integer. Non-negative integer is another way to say whole number. All right, what about this one? Is it a polynomial? Look at the coefficients. 8, negative pi, 6/7. Are they real? Yes, they are. Negative pi is a strange, kind of maybe a bit of a strange coefficient, but it is still a real number. And look at the exponents, 6 and 2. Are they whole numbers? Yes, they are. So it is a polynomial. What is the degree of this polynomial? The highest exponent is 6. Polynomial of degree 6. Okay, next concept. Form a polynomial whose zeros and degree are given. All right, here is what you must do. So this time they are giving us the zeros, and we have to make a polynomial that has those zeros. You know, before we kind of been used to being given a polynomial and finding the zeros of that polynomial, but this time we're working our way backwards. So we have a 0 of -2. That means x equals -2 is one of the solutions to the polynomial, and its multiplicity 1, so it just occurs once. And we have -3, x equals -3 with multiplicity 2. That means that occurs twice. Okay. So what must be what we do is we turn these into factors. All right. So rewrite zeros as factors. All right, so x equals -2. How do I write that as a factor? I move the -2 back over there with the x. So it's going to be what? X plus 2 is going to be the factor for that. What about x equals -3? It's going to be x plus 3. And since that occurs twice, I'm going to have x plus 3 occurring twice as in the factorization. Now, I just distribute everything. So I've got to distribute all this. I think I'm going to go ahead and distribute those first. It doesn't really matter what order you distribute these in. I could have distributed these first, but it's fine whichever way you do it. If I go ahead and distribute those, I'm going to get x squared plus 6x plus 9. Okay? Right, x squared plus 3x plus 3x plus 9. So let's combine the like terms, x squared plus 6x plus 9. Then I have to distribute the x plus 2 with that. So that's going to, I got to distribute it like that, right? So it's going to be, x cubed plus 6x squared plus 9x. Then I got to distribute the 2 like that. So it's going to be plus 2x squared plus 12x plus 18. Okay, some people do like to do like a box where they put the x and the 2 on the left side of the box and the x squared, the 6x, and the 9 on the top of the box. And that's a totally fine way to do it. If that's what you like to do, definitely do that. That's totally fine. I combine like terms now. X cubed, the 6x squared and the 2x squared makes plus 8x squared. The 9x and the 12x makes plus, what is that, 21x plus 18. So this is my answer. Let me go back and type that in. X squared plus 8x, x cubed plus 8x squared plus 12x plus 18. I hope I can remember all that. X cubed plus 8x squared plus, was 21x, right? 21x plus 18. I hope I'm remembering that right, but let me just go back and make sure. X cubed plus 8x squared plus 21x plus 18. Yep. And that's how you do it. Next question. For the polynomial function below, list each real zero and its multiplicity. Determine whether the graph crosses or touches the x-axis at each x-intercept. Determine the maximum number of turning points on the graph. Determine the end behavior. That is, find the power function that the graph of f resembles for large values of f of x, for large values of the absolute value of x. Okay. So the real zeros of f are just going to be based on the factorization here. So the -6 in front of the whole thing does not affect the zeros at all, but the x minus 6 means that I have one of the zeros to be what? 6. And then the other zero will be come from the x plus 9, and it's going to be what? -9. So those are my zeros, and I just got them from thinking about these factors. If I set them equal to 0 and solve them, I would get +6 and I would get -9. All right, the multiplicity of the larger zero, is actually the +6 because 6 is larger than -9. So the multiplicity of the 6 is 1 because it only occurred once. The multiplicity of the smaller zero, so -9 is the smaller zero. The multiplicity of -9 is what? It is 2 because x plus 9 was squared. So it means that you got x plus 9 and x plus 9 again. So that one occurred twice. So the multiplicity of that one is 2. So the graph does what to the x-axis at the larger x-intercept, which was 6? The multiplicity of 6 was 1. So what does it do when the multiplicity is odd like that? It crosses there. And it does what at the -9? Since the multiplicity is even, it touches there. Okay, the maximum number of turning points. Now I need to teach you another concept. So let's go back to here. Okay. And I've got a graphic for you to explain that. All right, the minimum degree is related to the maximum number of turning points. Okay, the minimum degree, if you know the degree, you can get to the number of turning points by subtracting 1. So if the degree is 5, the maximum number of turning points you would have would be 4. You might not have up to 4, but you could have up to 4. You might have 3 or 2 or 1 or whatever, but if you have a degree of 5, subtract 1 from that, and that'll give you the maximum number of turns you could have in the graph. So likewise, if you're looking at the graph and you know the number of turning points, you can know what the minimum degree is by adding 1. So let's say you had x to the 6 minus 2x squared plus 1. The degree is 6. So the number of turns would be 5. Of course, that's the maximum number of turns. That's the maximum number of turns it can have. It that might not have it that many. Or if you were looking at a graph that looked like this, count the number of turns. 1, 2, 3, 4. So the turns would be 4. So the minimum degree would be 5. That's how that works. Now let's go back to our problem and answer the question. The maximum number of turning points on this graph is what? Well, what is the degree of this polynomial? It might not be very obvious to you, so I'm going to have to point that out to you. You have to imagine if you were to distribute. Imagine distributing. Okay, you'd have an x minus 6, an x plus 9, an x plus 9. If you were to distribute all this, right, and then take that and distribute it with that, what's going to be your highest exponent? Well, you've got 3 different x's that are going to be multiplying together eventually with the distributing. So you're going to end up with an x cubed, right? And there may be several other terms there, but the only term that matters is the x cubed term. It also may matter eventually that there's a negative 6 in front of that whole thing. So let's just say negative 6x cubed. It doesn't matter for this next answer, but it will matter for an answer in a minute. So since x cubed is the degree, there's your degree, then the turns, the maximum number of turns would be 2. Let's go back and answer our question. Maximum number of turning points on this graph is 2. Type the power function that the graph of f resembles at large values of the absolute value of x. That's a complicated sounding question, but it's actually pretty easy. It goes back to what I said before. The power function that this is going to resemble for large values of x, in other words, the only thing that matters for the end behavior is this leading term here. The negative 6x cubed is going to determine everything about that function. So that's the answer. It's going to resemble negative 6x cubed for all of those large values of x. In other words, for the end behavior. All right. Again, list each real zero. The zeros here are going to be positive 3 and negative 2. The larger zero would be the 3. The multiplicity of the 3 is 3 because it occurs 3 times, x minus 3 cubed. The multiplicity of the smaller zero, negative 2, would be 2 because it's x plus 2 squared. So at the 3, the larger x-intercept is the 3. Since the multiplicity is odd, it's going to cross the x-axis there. And the smaller x-intercept is 2. And since the multiplicity is even, it's going to touch the x-axis there. Okay, again, the maximum number of turning points, you have to imagine if you were to distribute all this out, you've got an x minus 3 and another x minus 3, and another x minus 3, and an x plus 2, and another x plus 2. So altogether, that's 5 x's that are going to multiply together to get x to the 5th as the leading term. So if x to the 5th is the leading term, then what is the maximum number of turning points? It's 1 less than that. It's going to be 4. And the power function that this is going to resemble for large values of x is just going to be what that leading term is. And it's just going to be x to the 5th. Okay, x to the 5th. I didn't type it in right. Let me type that again. X to the 5th. All right, determine whether the graph could be the graph of a polynomial function. If it could be, list the real zeros and state the least degree the polynomial can have. This does look like the graph of a polynomial. A polynomial just kind of goes on forever, and it can have some terms in there. I'll tell you more about, it'll be easier to teach you what the polynomial graph is not once we get to one that is not a polynomial. So this is a polynomial function, and the real zeros are what? The real zeros, where does it cross? It crosses at -1. It crosses, let me look at it. Let me look at a bigger version of this. It crosses at -1 and at 3 and at 4. -1, 3, and 4. The least degree, we have to count the number of turns. How many turns do we have? There's a turn, and there's a turn. So every time you have an extrema, or you could say it this way, every time you have a maximum, a local maximum and or a local minimum, that is a turning point. So how many turns do we have? We have 2. 1, 2. Therefore, the minimum degree would be 1 more than that. It would be 3. Okay, decide which of the polynomial functions in the list might have the graph below. Okay. Let's talk about this. Okay, if we have one of our zeros being here, another one being here, and another one being here. All right, this 0 right here is going to be a factor of simply x. Oops, I got the wrong pen there. It's simply going to be x. It's just x equals 0. If 0 is the thing, then it's not like x minus 1 or x plus 3 or anything like that. It's just x. So that one is just going to be x. Now, because it touches right there, right? Then it's going to be an even multiplicity. Okay. Even multiplicity. Which means this is not just going to be an x, it's going to be an x to an even power. It can be x to the second, it can be x to the 4th. But I think for simplicity's sake, it's just going to be x to the 2nd. Okay, what is this factor going to be right here? What could give me an answer of x equals 1? That's going to be x minus 1. And that also touches. So that's also even multiplicity. So it's also going to be x minus 1 to the 2nd, or to the 4th, or to the 6th, or to the 100th. But I think it's just going to be to the 2nd for simplicity's sake again. All right, what about here? There, it crosses. So that's going to be odd multiplicity. So then what's that going to be as a factor? It's going to be x minus 2. And it could be to the 1st, or it could be to the 3rd, or the 5th, or the 37th. as long as it's an odd number. But I think it's just going to be to the first power for simplicity's sake. Notice that the right arm is up and the left arm is down, so I'm going to have a positive leading coefficient. Now let me go back and see what answers kind of match up with what I've said. X squared, x minus 1 squared, x minus 2. All right, let me look at these answers. Maybe I had them to look at here. Yeah. All right. X squared, x minus 1 squared, x minus 2. There's a good answer. I think that's the only good answer. Yeah. None of the other answers can work. So that's going to be the only answer. So let me put that answer in there. It could have been that more than one of these might work, but in this case, only B is a good answer. All right. Analyze the polynomial function, complete parts A through H. Determine the end behavior of the graph of the function. All right, again, imagine distributing this out. You don't actually have to distribute it, you just got to imagine distributing it. Okay, if we were to distribute this thing, it's going to be like an x cubed again. It's going to be an x cubed, and it's going to have some other terms. In this case, it's just going to be x cubed minus 5x squared. But even if it did have more than terms than that, the only term that matters for the end behavior is the x cubed. So the graph of f behaves like y equals x cubed for large values of the absolute value of x. Find the x-intercepts of the graph of the function. Find the x-intercepts. The x-intercepts are when I set the y value equal to 0. So if I set the y value equal to 0 on this thing, that means that I am putting 0 in right there. And I'm solving for x, which means I set that equal to 0. And I solve. And I get x equals 0. And I set that equal to 0. And I solve. And I get 5. So 0, and that occurs twice, and 5, that occurs once. Zero and 5. To do the y-intercept, I plug in 0 for x. So if I plug in 0 for x, that means I'm plugging in 0. Let me get a different color. Plugging in 0 here and here. So if I do that, that's just going to be 0. Squared is 0, and 0 times anything is still 0, so I'm just going to get 0. So the y-intercept, if I plug in 0 for x, is just 0. That won't always be the case, but it is the case here. Determine the zeros of the function and their multiplicity. Well, the zeros of the function are the same things as the x-intercepts. 0 and 5. Notice it says only type each answer once. The smaller zero of the function, so the 0 itself, that 0 has multiplicity too, because it's an x squared. So the graph of f does what? It touches the graph at x equals 0. The larger 0 of the function is a multiplicity 1, because it's the 5 and it only occurs once. So the graph crosses at x equals 5. Okay, you can graph the function, but I think I could just kind of know what the function looks like without having to graph it in my calculator. But if you want to, go ahead and graph it in your calculator. All you have to do is just type that in. Type that into y1 and set your window, like your x min would be -20, your x max would be 20, your x scale would be 2, your y min would be negative 50, your y max would be 50, and your y scale would be 10. But I think I can figure out what this looks like. It's going to touch at 0. So A is not right because it crosses at 0. It's going to touch at 0. It's going to cross at 5. So since this thing goes all the way to 20 and it counts by 2s, 2, 4, 6, that is crossing at 5. So B and C could work for that reason, but since this is going to be a positive leading coefficient here, if I distribute it, it's going to be a positive leading coefficient. The right arm points up, not down, so B is the correct answer. Approximate the turning points of the graph. Round the coordinates to the nearest whole number. I can do that just by looking at this. One of the turning points is 0, 0. Again, I'm just looking at this graph right here. Let me make it a little bigger. 0, 0 is one of my turning points. This is counting by 2s. This is counting by 10s. So that looks like it's around 3 or 4. And this looks like it's around 20. Negative 20, that is. So 3, negative 19, it looks like it's another turning point. Of course, if you're doing this in your calculator, you can just get the exact coordinates of the turning point, or at least close to it, by doing second calc maximum and second calc minimum, and you can find those turning points that way. Use the above information to draw a complete graph of the function by hand. This is kind of redundant because this looks so much like what we've already done. It's just going to be choice A. Find the domain and range of the function. The domain of all polynomials is all reals. So I think we would have to type in interval notation. So it's going to be negative infinity to infinity. Negative infinity to infinity. And the range of the function, since this one goes up forever and down forever, the range is going to be the same thing. On which intervals is the function increasing? Okay, let me look back. It's increasing from negative infinity on the x-axis until 0 on the x-axis, and it's also increasing from negative 3 on the x-axis to positive infinity on the x-axis. Negative infinity to 0, and 3 to infinity. And the interval of decrease, if I look back at this, it's decreasing from 0 on the x-axis to 3 on the x-axis. 0 to 3. And that finishes up that question. This one's easy. If f is a polynomial and x minus 5 is a factor, then f of 5 would be 0. Because if you plug in 5 for x, 5 minus 5 is 0. Okay, I think that's a good place to stop for part 1 of this video. We've gotten to through question 18. I will pick up on question 19 in part 2.